Okay, this is multivariable calculus, and in this lesson, I'm going to talk about sections 13.1 and 13.2. So in 13.1, we're going to talk about vector functions and space curves, and then in 13.2, we're going to start talking about some of the basic calculus of working with vector functions. Now, the ideas behind this are really just a combination of what we did back at the beginning of the year when we talked about parametric equations and vectors. So we did a lot of that in 2D. Well, now we're going to go through that same idea working in three-dimensional space. So it's going to really meld together what we did back in chapter 10 at the beginning of the year with what we did in chapter 12 when we went through all of that 3D coordinate system and equations of lines and planes. So vector functions are pretty simple because essentially what you do is you have a function that just has components to it. So typically we're working in a 3D coordinate system, and you can see here when I write a vector function, all I'm going to do is essentially have a function defined for the I component, a function for the J component, and a function for the K component. Similar to when we worked in 2 dimensions, when we're thinking about how do we go about working with this type of a setup, the nice thing about having a parametric setup or this vector component setup is that I can deal with each component independently of each other, and it allows me to break things apart in different ways. And where this really becomes very useful is if you think of, for instance, motion problems. So if I'm thinking about motion in space, if I can isolate things to just one particular direction, then it makes it a lot easier to work with. So at the very beginning of motion problems back in, when you were doing like Calculus AB or the first semester of Calculus BC, we did a lot of vector ideas, but we were only working in a single dimension, so we didn't even really deal with it in vectors. So then at the end of BC, we started to get into some things with parametric equations and start to look at, okay, how do we deal with the X and the Y independently of each other? And now all we're doing is adding a third component to that, dealing with the X, the Y, and the Z. Okay, so if I look at, for example, this vector function R of t, you can see the components are t, t squared, t cubed. So remember, going back and forth between a vector form and a parametric form is very easy, because all I have to do is just understand that, in this case, x of t is just that t component, y of t would be t squared, and z of t would be t cubed. Okay, so it's not difficult to do. And then if I need to do anything with that, if I want to figure out, let's say, again, from a motion problem perspective, if I want to know what's the velocity in the x direction, what's the acceleration in the x direction or in the y direction or the z direction, I can deal with all of those individually, or I can find all of those calculations at the same time. It's actually very, very simple to do. So one of the things we're going to talk about here is the idea of limits and continuity. Now, everything that we talk about here in 3 dimensions, it's going to be the exact same idea as what we did in 2 dimensions when we were doing calculus. So when I evaluate a limit, the only difference now is, since I have a vector function, I just need to take the limit of each component independently. So for example, again, we have this vector function, R of t is f of t, g of t, h of t. If I want to find the limit of that function as t approaches some value, I just apply that limit to each of the components independently. Okay, so here's an example of that. Find the limit as t approaches 0, and it says r of t is equal to 1 plus t cubed I plus t e to the negative tj plus sine t over tk. So essentially what I'm going to do here is, if I want the limit as t approaches 0 of r of t, that's essentially going to be the limit as t approaches 0, and I'll put this in component form. The limit as t approaches 0 of 1 plus t cubed, and that would be my I component. And then I would have the limit as t approaches 0 of t e to the negative t power, and that would be my J component. And then same thing for the K component. I'm just going to have the limit as t approaches 0, and I'd have sine t over t. and that would be my K component. And now I've got it in the correct form. Typically, I wouldn't even write this out. I would just go through and apply the limit to the three components, but I just want to make it really clear what's happening here. So at this point then, when I take the limit of each piece of this, you can see that for the I component, I'm going to get 1, so it's just 1 times I. For the J component, when I take the limit of that as t approaches 0, I have 0 divided by 1, so it's just going to be 0. And I guess I should probably write it this way. I'll just write it as 1, 0, and 1. Because remember, the limit as t approaches 0 of sine t over t is 1. Okay, so for this first example, what I'm going to do is I'm going to take the limit of a vector function here, r of t. And you can see that r of t has been defined. I've got an I component, a j component, and a k component. So essentially, when I take this limit as t approaches 0, I'm going to write this in component form. All I would do is essentially, for the I component, I'm taking the limit as t approaches 0 of 1 plus t cubed. For the j component, I'm taking the limit as t approaches 0 of t e to the negative t power. And for the k component, I've got the limit as t approaches 0 of sine t over t. Okay, and then this is really simple at this point. The limit as t approaches 0 of 1 plus t cubed is just 1. The limit as t approaches 0 of t e to the negative t, that'd be 0 over 1, so that would just give me 0. And then for the last component, the limit as t approaches 0 of sine t over t, that's my k component, that's going to be 1. Okay, so as a result, for my limit is now going to be a vector, where before, when we were dealing with limits, we typically got one single value. We never really looked at this in 2D, taking limits when we had, an I component and a j component. But regardless of how many vector components you have, you just take the limit of each component separately, and that gives you the result. So it's pretty simple to do. I showed very, very simple limits here. When you are working through your assignment, you might have some functions that are a little bit more difficult to take limits of, but what I'm trying to do is focus on the overall picture and not get so bogged down in some of those operations that you should be remembering from AB and BC calculus. Okay, so we consider a vector function to be continuous if at the point where we're trying to evaluate continuity, if the limit value is essentially equal to the vector function value. So it's exactly the same as before. When we did continuity before, when we were dealing with x and y, we had 2 dimensions. We said the limit value has to equal the function value in order for the function to be continuous. Now we're just doing that for a vector function. It's the same idea. The limit value has to equal the function value. Okay, so nothing different. Now, another thing we're going to start to get into here is what we call a space curve. So a space curve, it's a lot like when we were dealing with parametric equations in 2D, and we would have the x component in terms of t and the y component in terms of t, and then we could graph it on the calculator, and you could look at the x and the y separately. Well, now the only thing we're doing is we're bringing the third dimension into that. So when you're graphing these things, if you're going to do it by hand, which we won't do that very often, but if you were going to graph it by hand, you would have to find an x, a y, and a z coordinate for every single t value, and then you could plot those points and you could create the curve. So when we write these as a space curve, as a vector space curve, what we do is we just write it as a vector, and the t value, if you don't define any sort of boundaries for the t, then that means t can be anything. So you can see here, looks like I've got a period instead of a comma, but that should be 1 minus t, 3t, 2t. And you can see that I can also think of that written out without the component form, without that shorthand form. And in the end, when we graph this thing, all we would do is get some different points. And you can see what they did here to create the graph of this curve. They just said, okay, I know that this is going to be a line because all of these pieces are linear. So for each line, all I really need is 2 points. So we started with the obvious point when t is 0. And then they said, okay, when t is 1, there's my second point. And notice how they put that rectangular prism in there, not because the graph is a rectangular prism, but just so you could see the direction that the line is pointing it. It sort of orients that line in space so that the person looking at it can understand which direction that it's pointing. Okay, so we've got another question here that says, find a vector equation and parametric equations for the line segment that joins these 2 points. And we've already done stuff like this, right? We got a vector equation of a line. We did this in the last unit. So the only really difference now is, or the only real difference now is that what we're trying to do is we're trying to get the parametric equations as well. So we already know that if we're going to find the vector equation of a line, we start with the point where we originated, which is the point 1, 3, 2. And then we also need a direction vector. So for our direction vector, we're always going to multiply by some parameter t. And then to get the direction, I just find the change in the x, the y, and the z coordinates, or the ij and k components. So in this case, we went from 1 to 2. That increased by 1. We went from 3 to -1. That went down by 4. And then we went from 2 to 3. So that went up by 1 as well. And that would be my vector equation of the line. Now, I could also write it as a parametric. X in this case would be 1 plus t. Y would be equal to 3 minus 4t. And z would be equal to 2 plus t. So it's exactly the same as what we did in 2 dimensions, now just expanding it to 3 dimensions. So not anything difficult. And part of the reason we're going through 2 sections today is because most of this stuff is very, very simple. All right, so the next section focuses on derivatives and integrals of vector functions. So again, it's the same idea as what we talked about in the last section, where essentially what we're doing is we're taking what was true in 2 dimensions and we're showing and assuming that the same things are true in 3 dimensions. So when I want to find the derivative of a vector function, you can see what they're showing here is the definition of a derivative of a vector function. Well, it's the exact same as the definition of derivative that we had before. It's just that you would deal with those individual components, and that would allow you to then get the derivative of the vector function. So in the end, essentially what you do, like it shows in this theorem, is you just take the derivative of each component separately. So it's a very, very simple process. Okay, so I've got an example down here. I've got t squared I plus e to the tj minus 2 cosine pi tk. It says find r prime of t. So if I want r prime of t, all I've got to do is take the derivative of each one of those components. The derivative of t squared is 2t. The derivative of e to the t is e to the t. And the derivative of that negative 2 cosine pi t, well, when I take the derivative of cosine, I'm going to get negative sign. So I've got a negative and another negative, so that's going to give me, in the end, when I do my chain rule, I'm going to get 2 pi sine pi t. Now, I could have written it in this expanded form, but I like to use the component form when I can. I think it's just a little bit more concise. So that's how I'm typically going to write the solutions. And like I've mentioned before, you can use whatever form you want when you write it. The important thing is you need to be able to read all the different vector forms that you might come across. All right, so the next question is a little bit more of an application. It says, find parametric equations of the tangent line to the circular helix x equals cosine t, y equals sine t, and z is equal to t. So one of the things you're going to have to do that I didn't really go through in here, but you'll see it in the assignment, is you have to be able to try to visualize what type of graph is being created here. And so if you went and looked at this in 2 dimensions, so don't think about the z for a second. If we had x as cosine t and y as sine t, you should know that that's going to create a circle. So I've got a circle in the x and the y direction. So as t changes, I'm sort of tracing around a circle. But also as t changes, I'm going to be increasing the z value, assuming that t is increasing in size. So that's going to create what we call a circular helix. So if I looked at it from above, it would look like a circle. But if I look at it from the side, it sort of looks like a spring that's been stretched out a little bit, because I've got that circular shape, but those curves are all separated out as it spirals upward. Okay, so they asked us to find parametric equations for the tangent line at the point where t is equal to pi. Okay, so this is very simple to do, finding the equation of a line. Remember, just like before, when we want the equation of a line, we need a point and we need a slope. So I know that my vector function here would be equal to cosine t, sine t, t. And if I want the derivative, because I'm going to need the derivative, I just take the derivative of each component. Derivative of cosine is negative sine. Derivative of sine is cosine. And derivative of t is 1. So that's the derivative. That's going to tell me the slope at any point. And notice that we get a slope essentially in each direction. And I want to evaluate this at pi. Well, at pi, the sine of pi is just 0. Cosine of pi is negative 1. And then that third component is always 1. Okay, so then the other thing we would need there, if I want to find the actual equation for the tangent line, then I need to know the x, I need to know the y, and I need to know the z. Okay, so it's at the point where t is equal to pi, and we're supposed to be finding the initial point being t naught. So what that means is my initial x coordinate would be cosine of t naught. My initial y coordinate would be sine of t naught. And my initial z coordinate would be t naught. So then, just like we did the vector equation of the line before, we did the initial position plus then t times our direction vector. Well, our direction vector, we just found it right here. That's my direction vector. So let's just think about this component by component. So for x, I've got cosine of t naught, and then I'm going to add 0 times t, because nothing really changes there. And then I've got y is equal to, so I have sine of t naught, and then my change in this case is going to be minus 1 times t or minus t. And then for the z, we started at t naught, and we're always going to add t to that. So now, let's say my initial point, I want t to be 0. Well, then I know the initial point would be at cosine of 0, which is 1, sine of 0 is 0, and then z naught would also be 0. And then I can go to t is equal to 1, and then I can get a new coordinate off of that. So if I knew what t naught was, now I can work off of it and I can create that curve. All right, so what you'll notice down below here is I have a bunch of the derivative rules listed out for you. And the main idea behind this is that primarily the derivative rules that you learned back in Calculus AB and Calculus BC, it's the same derivative rules. The only things that are going to be a little bit different is that we do have a couple of operations with vectors that are unique to vectors, and that's when we're dealing with a dot product or when we're dealing with a cross product. So if you notice there, those rules work very much like the product rule did before. So that's essentially how you're going to work those out when you're taking the derivatives. It's like the product rule, even though you've got that dot product operation and that cross product operation in there. In the end, the rule works out essentially the same way. Okay, so let's take a look at integrals. So just like we did with derivatives, integrals work essentially the same way. If I want to take the integral of a vector function, all I have to do is integrate each one of the components independently. So notice what I have here is a vector, or excuse me, an integral that's going over the interval a to b. So then I'm just going to integrate each component over that same interval to get the result. So this is pretty simple to do. So let's look at an example. We've got r of t is equal to t squared I plus e to the tj minus 2 cosine pi tk. and it says find the integral from 0 to 1 of r of t dt. Okay, so I'll just show this, but really you can kind of tell what we're going to do here. And I guess I don't really want, I want r of t, but I want the integral of that. So r of t dt would be equal to, and I'll write this in component form. So in component form, I'd be taking the integral from 0 to 1 of t squared dt. And then I would be taking the integral from 0 to 1 of e to the t dt. And then the integral from 0 to 1 of negative 2 cosine pi t dt. So that's usually how I write it out. You could also write it out as a single integral with all of the components in there, and then have the dt outside of that. It just depends on your preference. I usually do it separately like this. So in the end, I'm not going to show you all the steps. You guys know how to integrate. In the end, when you go through the process here and simplify down, you're going to get 1/3 for that first integral. You're going to get e minus 1 for the second integral. And you're going to get 0 for the third integral. So I would have 1/3 e minus 1 and 0. And remember, this is my I component, j component, and k component. So it's not difficult to do. A fairly simple process. It's just really a matter of what notation do you want to use. Like I said, I'm typically going to use that component notation just because it tends to be a little bit more concise. So I put a couple more examples here for you that I just wanted you to quickly try. I think you'll find this pretty easy. The one thing I'll warn you about, I gave you some pretty easy examples to work here. When you start doing these types of problems in your homework, all of the integration techniques are open, meaning that they could all show up. So we're talking about substitution, integration by parts, partial fractions, trig substitution, all those different things could show up. So some of these will be really simple, like these examples that I gave you. Some of them are going to get a little more complex where you're going to have to remember some things from BC calculus. So take a few minutes, so pause the video, take a few minutes, work out these integrals, and then when you come back, I'll show you the solutions. Okay, so here's what you should have come up with. I didn't show the steps because, again, you guys know how to work these types of problems. But for the first one, you just get j, or I could have written 0, 1, 0. Just wanted to show you the two different ways you could write the answers. And then for the second one, we got e squared minus 1 over 2, e minus 1 over e, and 1/2 as the three components. So not really too tough to do. There's not too much in terms of application problems just yet. What we're going to do when we get to section 13.3 is we're going to get into talking about arc length and curvature. And then the section after that, we're going to start doing a bunch of motion problems. And when we do motion problems, this stuff will all start to really fit into your intuitive ideas of how things should be working. So right now, we're more focused on the operations as opposed to actually getting into any application problems.